Guys, welcome to inverse functions and relations. So the essential understandings that we need to look at today are inverses of functions. Inverse of a function may or may not be a function. Number two, if you square both sides of an equation, multiple solutions could arise. And finally, if you can show that f of x and f of x are inverses, that means you can show that their composites are equal to x. Okay? And the last thing, the range of the function is the domain of the inverse. So we got to think about a function and the y values, and when you talk about inverses, you're actually switching x and y. So what the last part says is, well, if the original function's y values become the inverse's x values. So we'll look at a few examples here. In example 1, okay, what is the inverse of the relation S? Now, the key thing here, a relation is just a collection of terms. In this case, it's a collection of ordered pairs. So let's look at our relation S. Here are our ordered pairs. X's are 0, 2, 3, and 4, and they're mapped to -1, 0, 2, and 3. So how do we find the inverse? Well, from a table of values, finding the inverse of a relation from a table just means switching the x and the values of x and y. That's all you have to do. So when we look, notice how instead of writing x, y, I put yx up here because look at my y values now are the x values and my x values are now the y values. So right here, this is the inverse function, or this is the inverse relation, okay, of the relation S. So this would really be S inverse. If you wanted to call it, you would say S inverse. Okay, it's not S to the -1 power, it's called S inverse here. Now, in the second example, we're going to take this idea and we're going to go a little bit further. So what is the inverse of y equals x squared plus 1? So we're going to switch x and y like we did with the table. But once you do that, you're not done. You have to resolve the equation for y, and then we got to talk about the domain and range. So y equals x squared plus 1, I just rewrote my equation. First step, like the table, switch your x and y values. And then you have to resolve the equation for y, so it really becomes a literal equation. So I subtract 1 from both sides, and then I square root. You always get plus or minus the square root. Okay, so the plus or minus the square root of x minus 1 is equal to y. So that's my inverse. So instead of writing y, you could say f inverse here. Okay. Now, the important thing to remember here, this domain is x minus 1 has to be greater than or equal to 0. So the domain is x is greater than or equal to 1. And be careful, normally we just talk about the principal root here. So y equals the square root of x minus 1 would be the inverse. Okay, so you don't always see that plus or minus when you do the inverse of a quadratic function. All right, so consider the function in this example, f of x equals the square root of x minus 2. Now, in this case, the domain of f of x would have to be greater than or equal to 2. Okay? And so we want to know what the domain is, range is. So really, remember, when we talk about domain and range, you have to look for fractions and you have to look under radicals. We have a square root, so we have to look under the radical to the radicand. The radicand has to be greater than or equal to 0. So we set x minus 2 greater than or equal to 0, so that means the domain x has to be greater than or equal to 2. Well, if you plug in 2, you get 0. So that means the domain the range, starts at y is greater than or equal to 0. So there's your domain, there's your range. Part B, they want us to find the inverse. Okay, so I write my equation y, instead of writing f of x, I write y equals square root of x minus 2, and that's just a notational thing, okay? It's no longer in function format, okay? So then I switch x and y out, which I did in step 2 right here, and then I resolve the equation for y. So I have to get rid of the radical first. It's a square root, so I square both sides, and then I add 2. So my inverse, okay, my new y equals, so my inverse here is just x squared plus 2. Now, when we talk about the domain and range, the domain here is going to be a little bit different. It's a quadratic equation. Notice how x has to be greater than or equal to 2 here. That's the domain. So that's the range of this function. So the range of this function, okay, is y is greater than or equal to 2. They switch spots. And the domain, in this case, would become it's really actually all real numbers, okay? But if we switch here, we would say x has to be greater than or equal to 0 when you switch x and y, okay? But it is a parabola, it is a quadratic, so the domain there would be all real numbers. The range becomes y is greater than or equal to 2. That's actually the vertex. When you talk about the range of a parabola, it's got to be where the vertex is. Start where the vertex is, excuse me. All right, so now, we talked about this before, a one-to-one function, and the idea here is if you think about a function, every x corresponds with one y, okay? Meaning, if you talk about the birthday function and you say, well, every person has a birthday, okay? And we want every person, it's okay to have different people to have the same birthday, but one person like myself can't have two birthdays. So x cannot have two different outputs. Okay, that wouldn't be a function. And the idea maps here to one. So to be a function, every different input has one output. They can repeat, but every different input has one output. Here, when you talk about one-to-one, every y value corresponds to only one x value. So there's only one x going to the y coordinate. That's what it means to be one-to-one. So for example, if we look at a parabola, a quadratic here, it's not one-to-one. Here are all our y values. We want every y value to only have one x, okay? And it's got to be the same. It can't have two answers. So if you look here and here, 4 has two different values coming to it. That y value has two different x's. It's got 2 and -2 coming to the same spot. So that means it's not one-to-one. A function that would be one-to-one is like linear, a cubic function. Okay, an easy way to tell if a graph, from a graphical standpoint, so tabular, you're looking at if a y value has two different x's going to it. You're going to see that a lot with quadratics. Well, quadratics in like 4th degree, 6th degree. But if your function fails the horizontal line test, so if you draw a horizontal line and that horizontal line touches it twice, touches your graph twice, you're not one-to-one. A mapping diagram looks, and I have here, so 4 has 2 arrows going from it. You're going back to x, so you know it's not one-to-one. So just like the vertical line test shows you if a relation is a function, the horizontal line test tells you if a relation is one-to-one. Parabolas, quadratics are not one-to-one. Last example, we have a couple parts here. You have for this function 1 over x minus 1, find the inverse, and then see if the inverse is actually, if they are inverses of one another. So like before, you switch x and y, and you resolve for y. Now this is a little more challenging. So what I did here is I set up a proportion, and you don't see that here. It's very subtle, and I cross multiply. So that's why I get 1. 1 times 1 is 1, and then I take x times this quantity. Okay, well then I divide by x. I don't distribute the x, I divide by x quickly, and obviously we know that in this case we can't let x be 0, okay? And then I have y minus 1 here, and then I just add 1 to both sides, so there's my inverse, and I can always say, hey, make it the inverse. Now, I do know this is the inverse. Mathematically we're correct, but let's just check. So f composed with f inverse. Now we've talked about composite functions before, so that's why I didn't redefine those composites for you. So what we have to do here is we plug one function into another. So our second function is the inverse. So whatever our inverse is, that goes back into the original. 1 over x minus 1. So the inverse is being plugged in for x, and that's what you see the parentheses. Here's 1 over x minus 1, but our x is known. It's 1 over x plus 1. So I plug that in. And notice how the 1's cancel, so you have 1 divided by 1 over x, which is just x when you simplify that out. So lastly, let's check the reverse now. F inverse times f of x, that composite. So f inverse of f. So now you're plugging your function f into the inverse that you think is the inverse. So you get 1 over x plus 1, but our new x is 1 over x minus 1. So then I rewrite it as 1 divided by 1 over x minus 1. When you divide two fractions, you flip and multiply. So 1 times x minus 1, which is just x minus 1. 1 minus 1 is 0, so you just get x. So those two functions, well, no, excuse me, those two are inverses of one another. I don't know yeah, I could see off the top of my head if this is if the inverse is a function, but let's just say these two are inverses of one another because we've shown that those two composites are equal to x. Now they have to be equal to x. If they're equal to 5, if 5 and this was 5, doesn't matter. Then they wouldn't be inverses. They have to equal x. Okay, so that's very important when you check to see if two relations are inverses. Okay, so that's all we have for today. If you have any questions or comments, just type them below, or you can email me at nicholas.bennett@dc.gov. Thanks.